Let's continue to understand Mr. Bernoulli. You remember in the previous video tutorial we established for a fluid potential energy, kinetic energy and pressure energy, ways to store the work put into that parcel of fluid. Now what Mr. Bernoulli said, the sum of potential energy and kinetic energy and pressure energy in one system must be constant. Now he wrote it a bit different. He took first of all our writing here, potential energy m times g times h, m times g times h, plus kinetic energy m half v square m half v square, and the pressure energy P times V, volume, pressure times volume, is constant. Now you can divide the entire equation by volume, or multiply with 1 over volume, and my result will be mgh over volume plus kinetic energy v square over volume plus pressure energy over volume is constant. Now the first thing we can do is we can cancel out the two volumes and we have the static pressure as a sole player. Second we can remember that our mass equals rho, that is our density of the matter, multiplied with the volume, because rho is mass over volume, right? Now if we apply this in this formula, it will simplify, and we have as a result m replaced by rho times volume times g and h over volume plus m again rho times volume v square over 2 volume plus pressure, that is constant. Now again we can simplify volume versus volume, volume versus volume. This is capital V, this is small v for velocity, and eventually the final version of the Bernoulli equation is rho times g times h plus rho half v square plus p is constant. So here's the height, the playing factor, and the second one is the speed, the playing factor, and the last one we talk about static pressure. Now if you look into the work where Mr. Bernoulli published his findings, that's called hydrodynamica or hydrodynamica, which talks about the power of water. When you look at the illustration, it is about waterworks, and that was what was bothering the towns of the 1700s. They had to improve their public works, their water systems. And when you think about this, you come up with piping. Piping looking a bit like this here, where you have a ground zero, and then maybe you have a height, which we will call y1, and another height, which we might call y2, and we can establish y2 minus y1 equals h, the height over here. So obviously when you lift a parcel of fluid from, let's say, down here to up here, you add to the potential energy, or this parcel of fluid gains rho g h. Same as here, there's a pressure 1 here, and there's a pressure 2 here, and because I'll call this a pressure 3. And eventually we have here an area 1, here we have an area 2, assume it's the same area 2 here. Then a fluid which flows through this part here, and so much volume goes through in 1 second, has to go much faster here in order to produce the same throughput, so much volume per second. That means there is a speed v1 and there's a speed v2, and we gain an additional kinetic energy rho half v square here, while v square is v2 minus v1. So we're trading this kinetic energy for potential energy when we go up here, and that's the whole Bernoulli equation. Now in aerodynamics, the situation is a bit easier. We have here one height, which we still call y, and since there's no change of height for the time being, there's no change of potential energy, so our rho g h becomes 0. Now our whole equation becomes a bit simpler. We have the fluid in here, and in here is the same parcel of fluid. This fluid has a pressure 1. Here we have an area 1. This one is area 2. In here we have a pressure 2. The fluid travels with a speed v1, and it travels here with a speed v2. So now, following Bernoulli, we can say that in this position here, rho half v1 square, the kinetic part of our equation, plus the pressure 1, and plus rho gh is 0, we can skip, equals the one on the right hand side, where there is rho half v2 square plus p2. Now we established that v1 is smaller than v2. In the smaller diameter, the fluid has to go faster in order to have the same throughput like in the bigger diameter. And the consequence out of this is that the pressure 2 needs to be less than the pressure 1, because v1 is less than v2. I say it again. Pressure 1 is now larger than pressure 2. Speed high, pressure low. Speed low, pressure high. That doesn't spring to your mind. Every one of us would have guessed differently. But with the law of the conservation of energy, which Bernoulli expressed in this Bernoulli equation, this is the consequence. We have a high speed of a fluid, the static pressure will be less. We have a low speed of a fluid, the static pressure is increased.